Hello. Welcome to this video where we will be extending the concept of the classical ball that we have seen in previous video to what we call it as quantum billiard ball concept. And the idea here is to describe the concept of interference, which makes quantum systems behave differently than the classical systems, and we will see by the end of this video how that is achieved. So to begin with, a quick formalization where we see on the left hand side we have the described classical system where the probabilities of vertices receiving or having the ball is 1/2. And on the right hand side, we have the quantum system where the probability distribution is represented by the amplitude, which is 1, which is 1 divided by under root of 2. Now, the important point to notice here in the quantum system is that we also have negative amplitude, which means if we end up squaring for probability distribution, we will end up getting the same probability as we see for the classical. So 1 by under root of 2 square is 1 by 2, and minus 1 by under root of 2 is also 1 by 2. Now we go further. Once we have described our state, now let's also describe our operators. In terms of classical, we have the operator in the L1 normalized, both rows and columns. So if you see either a row or a column in the left hand side, the sum total will be 1. In quantum, the columns are L2 normalized uh, in a sense that if you square the amplitudes and add them together, you will end up getting 1. Now, let's begin with taking our first step. In the classical systems, let's assume that we are starting from a position where the ball is at the vertices 1, which is represented by the vector representation 1, 0, 0, 0, and we applied the operator to reach to an state which is represented by 0, 1 by 2, 1 by 2, and 0, which means that the ball has moved the probability of ball being found at vertices 2 and 3. Similarly, for the quantum, if you see, we start with the same position as in vertices 1, applying the operator, and we end up with the amplitude of 1 by root 2, 1 by root 2 at the vertices 2 and 3. Of course, if you square the amplitude as said before, you're going to get the same probability distribution. Now, let's assume that we should take the second step where we start from x1, again applies the operator, and then see where we gonna end up. In case of classical, we now see that the probability distribution has shifted from 2 and 3 before to 1 and to the vertices 1 and 4, because now we have 1 by 2, 1 by 2 at the indices of vertices 1 and 4. But if you look at quantum, this has changed. If you look closely, now we have gone back to our initial state from where we started. Remember that we started with the ball being at vertices 1, both for classical and quantum. That's why the amplitude value probability was represented by 1 in the vector notation, and we have again came back to the same state. Why it is so? If you now just look at this mathematically, when you multiplied the operator with the factor notation for the quantum, you see that we have different probability distribution. And how did we arrive at a different probability distribution? That is because we now in the quantum state have something called as constructive and a destructive interference. So if you take the top row and if you multiply with the vector's magnitude, it will add up to positive, and that is resulting in a constructive interference. While if you take the bottommost row and if you multiply with the vector's magnitude, here we have -1 by root 2, and it will end up subtracting the value, and that's why we have destructive interference. Therefore, to summarize this, classical and quantum differ in the normalization type. We have seen L1 and L2 normalization type. And classical and quantums differs in using the real and complex number. So for example, we have seen in the mathematics of quantum mechanics what is the means and purposes of using a complex number. Therefore, to conclude, it must be understood that interference in the quantum system plays a very important role. I'll stop here. Thanks for watching, and I'll see you in the next video.